We're going to look at series, and I'm going to start this one off by giving you the difference between a sequence and a series. Notationally, a sequence might be written as curly brace a sub n. That didn't look like a good curly brace. That's okay. With a subscript looking n equals 1, and then a superscript looking infinity. And we would write this down as a sub 1, comma, a sub 2, comma, a sub 3, comma, dot, dot, dot. A series is written often in sigma notation. And here we have sigma, which means a sum. The sum as n goes from 1 to infinity of a sub n, and it will equal a1 plus a2 plus a3 plus dot, dot, dot. So here's the thing. Notationally, you've got a set for a sub n. For a sequence, for a series, we have sigma notation. Practically, the sigma means we're adding things together. So where a sequence has a bunch of commas, a series has a bunch of pluses. In other words, a series is a sum. Let's consider an infinite geometric sequence. The set of a sub n is equal to a times r to the n minus 1. We can find the sum of the first n terms, which, by the way, is a series, by writing out some terms. S sub n is equal to a would be the first term, plus a times r, plus a times r squared, plus dot, 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 we don't know how many, all the way up to a times r to the n minus 1. Now, for reasons yet unclear, I'm going to multiply both sides of this by negative r. So we end up with negative r times s sub n is equal to negative a times r minus a times r squared minus a times r cubed minus dot, 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 all the way up to minus a times r sub n minus 1 minus a times r to the n. I am now going to add together these two equations. Left-hand side, we get s sub n minus r times s sub n. Right-hand side, well, would you look at this? A bunch of terms cancel out or subtract out. And in fact, all of the terms subtract out except for a from the first one and negative a times r to the n from the second one. So s sub n minus r times s sub n is equal to a minus ar to the n. Factoring out and then solving for s sub n, we get that s sub n is equal to a times the quantity of 1 minus r to the n divided by 1 minus r. We had said that this was an infinite geometric sequence, and we just showed what would happen if we added together a finite number of terms. This will give a sum, but it's not the whole sequence. Or I should say it's not the whole series. It's not the sum of the whole sequence. For each n, s sub n is a partial sum for the series. Now we're going to get a little bit meta here. The set s sub n, right, set notation, it's really the series. S sub n, and it's given by s sub 1, s sub 2, s sub 3, dot, 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 up to s sub n. Now, let's talk about what these are. S sub 1 is the first term, right? S sub 2 is the sum of the first two terms. S sub 3 is the sum of the first three terms, and s sub n is the sum of the first n terms. This is a sequence of partial sums. The terms in the sequence are a bunch of sums, and so while each s is a series, by putting commas between them now, I have a sequence that's made up of partial sums. All of that was to help you understand the definition that we're about to write down. Given a series, sigma n equals 1 to infinity, right? So the sum as n goes from 1 to infinity of a sub n. Let s sub n denote its nth partial sum. So s sub n is equal to the sum as I goes from 1 to n. Now, before I write anything more, what's going on? We had n equals 1 down here to infinity, but now we're saying we're capping it at n, so I can't have n go from 1 to n. So I have to change the index to I. So the sum as I goes from 1 to n of a sub I, and a sub n changed to a sub I because that little subscript has to match the index. And S sub n is also represented as a sub 1 plus a sub 2 plus dot dot dot, don't know how many of them, all the way to a sub n. If the sequence of partial sums, that is the sequence of S sub n, is convergent, I'm going to redraw these curly braces. I can do a better job there. Anyway, if the sequence is convergent, and if the limit as n approaches infinity of S sub n is equal to S, and if that exists as a real number, and I put in parentheses as a finite real number, then the series sigma a sub n is convergent. And we write that a sub 1 plus a sub 2 plus dot 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 plus a sub n, but plus dot dot dot, we keep going, it's infinite, is equal to S. Or we say the sum as n goes from 1 to infinity, using sigma notation, of a sub n is equal to S. S is then the sum of this series. In order to bring this home a little bit, in the case of a geometric series, the sum as n goes from 1 to infinity of a times r to the n minus 1 is convergent if the absolute value of r is less than 1 and divergent otherwise. That's because if absolute value of r is less than 1, then the limit as n approaches infinity of a times 1 minus r to the n over 1 minus r becomes a over 1 minus r, because a fraction with a base less than 1 going with an exponent that's going to infinity is going to go to 0. So S is equal to a over 1 minus r. A final note here. Saying that the sum as n goes from 1 to infinity of a sub n is equal to S means that we can get as close to S as we want by simply adding enough terms.